Okay, now that we have the ensemble results from our Monte Carlo analysis, we can do something with those at the end of our script to be able to see what those look like. So something we haven't talked about before is a quick way to plot probability density curves. So what I'd like to do here is visualize my uncertainty and my parameters simply by looking at the raw distribution of the values of the y max and x half and see what those look like. So I want to put these in a new graphics window, so I'm going to start a new graphics device. And in this one, I'm going to actually plot two different plots. So I want to make this one a little bit higher or a little bit taller than it is wide. So I'm going to make the width 6, the height 8. Again, if you're running a height equals 8, there we go. If you're running a Mac, you would want to put a quartz here. But this is not going to work on my computer, so I'm going to comment that out. So there is a function in R called par that is a way to generically pass arguments to the plotting code or to the plotting device to make sure that they're all set up for the next time you want to call plot or lines or something like this. And there are many, many different arguments that you can send to par to get a plot to look the way that you want. One of the particularly useful ones if you're doing a multi-panel plot. So one way to do a multi-panel plot is to use the mfrow argument. An mfrow argument is expecting a vector of two values where the first value is the number of rows you want in the multi-panel plot. In this case, I'm stacking them on top of each other, so I want 2 rows, and then the number of columns, and I want 1 column. If you're curious why it's called mfrow, that just tells it whether it fills rows or columns first. If you call mfrow, it's going to fill rows first. If you call mfcol, it fills columns first. When you only have 1 column, it makes no difference which one you use, because it's only got 1 column to fill. So in this case, I could say mfrow or mfcol and have the same results when my vector is 2 and 1 like this. So the way that multi-panel plots work is then you just call plot for as many times as you want to fill in those panels. Again, according to mfrow or mfcol and whether it fills the rows or the columns first. So I'm going to call plot, and I'm going to call plot on the results of a call to the function density. Density is just a quick way to generate an object that represents a probability density function. And when you want to get that probability density function for a given vector of values you have or a given random variable, we just have to give it that random variable. So I want to go to my MC results data frame and go to the Y max column. So this will create a probability density function for the Y max column of this data frame, all of our ensemble values for every realization for Y max, and then it will plot the results of that density. So this is just a quick way to visualize a distribution with a nice smooth probability density function line. Now it's making some assumptions on how to do that smoothing, which are important to understand, but this should give us a pretty good perspective on what our uncertainty looks like. And we want to do the same thing for the Y max and the X half columns. And 100 realizations is not that many. So I'm going to jack this up to 1,000 for now. So we'll be doing 1,000 realizations. So let's see what this does. First of all, it'll be 1,000 red lines and a black line. Something interesting happened. Notice that we got a nonsensical solution for one of our realizations. So there's always a chance with an iterative routine and generating this error with random error, that we're going to create some weird random error with one realization that's really unlikely, but is going to create a situation where our NLS conversion cannot converge on a reasonable answer, in which case we got something weird going on here with our response to our curve. Now, with just 1 out of 1,000 realizations, that's probably not going to have a huge effect of our statistics, so I'm not going to worry about that. But in a little bit, I'll talk about how you might carry out this Monte Carlo uncertainty analysis, where you actually set the slope and the intercept for your first guess to be what you get from your first nonlinear regression, rather than letting it start at values, like in this case, we're starting at 1 for y max and 1 for x half. And when you start farther away from the right answer, you create a situation where there's a higher chance that it's going to go somewhere unreasonable. But anyway, I'm not going to worry about just one realization out of 1,000 and those effects on the statistics. You can see what these probability density distributions look like. We get a value that's centered on 10 for our y max. That should make sense. And we get a value that's centered about on 2 for our x half. Notice that these two distributions are not normally distributed. You have much more mass to the higher side than you do to the lower side. And this is a surefire sign that the propagation of uncertainty through your model is occurring in a nonlinear fashion. And this is exactly what a Monte Carlo analysis helps you conquer, and that the Monte Carlo analysis is giving you an honest appreciation of your uncertainty and the fact that it might not be a normal distribution. Whereas if you're using a technique that assumes that's normal, that would not be giving you an honest perspective on your uncertainty. And that's exactly why, if you go back to the Mitalski paper, they say you should not trust the uncertainty analyses that you get from an NLS type routine or from a nonlinear regression type routine, because it's making assumptions about the propagation of uncertainty through the model that it will be linear in nature. And it might be linear with some types of nonlinear models, but there's no guarantee that it is. So the better way to approach an uncertainty analysis with a nonlinear regression is to do one of these Monte Carlo approaches. Otherwise, your estimates of your uncertainty in your parameters could be biased. So how do we actually look at the numbers that are being calculated here? Well, we've got the full ensembles of both the parameter estimates themselves as well as the NLS estimate using the standard error of those parameters. And remember, it's that NLS estimate of the standard error that we should hold suspect when we're doing a nonlinear regression. So let's write just a little bit of code here that creates some variables that will make it easier for us to compare the NLS results versus our Monte Carlo results on that uncertainty. So I'm going to create a variable that I'm going to call ymax compare. This is just going to be a named vector with a couple of numbers in it. And as we did with the linear regression, I want to calculate the standard deviation of the ymax estimates, just using the SD function on MC results $ymax. And I want to be able to compare that quickly to the mean of the standard error of ymax coming from NLS. So I want to do a mean on the MC results $ymax standard error. And then I just want to do the same thing, but with x half. So to keep myself from having to type a lot of extra code, I'm going to cut and paste first and just change these to x half, x half, x half, x half. So now after I run this script, I can look at these variables and quickly see whether I get the same results, and also just to make this as robust as I can, I'm going to run it 10,000 times instead of 1,000 times. Now that is going to take a while to run. So I really hope I don't have any bugs in the code after the loop. Oh, I see I'm getting a couple or 3 weird results again. Again, as if there's just a few of them, and I'm not really going to worry about those messing with my statistics when there's 10,000 other values. It's really interesting. You might hear the fan on your computer crank up when you're running a lot of iterations. You're really putting it to work numerically. And you can see these distributions are a lot smoother now that I'm running 10,000, but you can still see that they're not normally distributed, which is a surefire sign if you start looking at these compare. Sorry, Ymax compare is what I called it. I get numbers that are different. I get, for the standard deviation of the Ymax from a Monte Carlo analysis, I get something like 0.94, and I only get 0.91 for the standard error in Ymax. And also I can do the same thing for x half compare, and you can see that I get 0.65 or 0.66 for the standard deviation from my Monte Carlo analysis and 0.64 for the standard error. And that is the type of bias that we're talking about when you see distributions like this from the Monte Carlo analysis. So the less normal this is, the less you should trust that standard error coming from the nonlinear regression tool. And in general, it's the Monte Carlo approach that, as long as you do enough iterations, is always going to give you an appropriate perspective on the propagation of uncertainty. So I hope that gives you some perspective on why I teach Monte Carlo analysis in this class, just because it's such a useful general tool for propagating uncertainty, and it requires no assumption about the nature of these distributions whatsoever to come up with a valid perspective on that uncertainty.